Ladies and gentlemen, let us turn to the last lecture of the day to be given by Nicholas Wormald from Monash University. Unlike the first three speakers who got their PhDs only recently, Nick got his PhD in 1979, but very soon after that he became one of the most important mathematicians working on random graphs. Ever since then, he has focused his attention on probabilistic combinatorics, especially random graphs, and he was also instrumental in introducing the differential equations method to track random processes in combinatorics. He's a fellow of the Australian Academy of Science. Ladies and gentlemen, please welcome Nick Wormald to deliver his lecture.
Okay, thanks for the invitation, the introduction, and I'd like to thank the organising committee for the invitation. It's a great honour to speak here. Okay, so although my PhD was a long time ago, I decided to talk about one of the topics in my PhD thesis, because I wasn't quite sure what to talk about, and this seemed like a good idea since I've got some new results there. Okay, so I want to talk about why do we count things. Don't Google that, you'll get a weird answer. You might be able to imagine what it is, but for mathematicians, why do we count things? Some of the past results on counting, graphs by degree sequence, and a conjecture, and the recent resolution of the conjecture and some implications. And I wanted to talk about the approaches here because basically if you look at the sub-theme, there's this theme of perturbation methods for combinatorial enumeration, which I've found quite useful. And if time, I'll talk about counting other things like Latin rectangles. So first of all, proving existence by counting. This is one of the reasons we count things. Here's an example of the basic probabilistic method. Suppose you have a 4 regular graph. Every vertex has degree 4, and or a 6 regular graph in this case, and we're going to colour it with 4 colours. So no 2 adjacent vertices have the same colour. Okay, well we can do that. For this graph, you can see it cannot be 3 coloured because there's basically a K4 there. There's certainly lots of triangles overlapping that prevent a 3 colouring. So we could ask, what if we prevent or forbid 3 triangles? Can we then 3 colour every 6 regular graph? Well, we can try to. Small ones perhaps. For small ones certainly we can. But by counting we can show that even if we forbid not only triangles but longer cycles up to any given fixed length, there are still 6 regular graphs with no proper 3 colouring and no such short cycles. And the proof is pretty simple if you think about, if you can count things, you count the 6 regular graphs, somehow count those having a short cycle, count those as 3 colourable somehow, or bound the numbers, you don't have to count very exactly here. And then what's left over, you can see by just subtracting the numbers that there's some things left over. We don't know how to find what's left over, so it's a bit like the dark matter in the universe. We know it's there, but we can't really find it. This gives no algorithm for finding what's left over. What's left over is going to be a 6 regular graph with no short cycle, and it's not 3 colourable. Okay, so there are lots of examples of the probabilistic method. In fact, Paul Erdős was accused of just counting things, but of course the probabilistic method has evolved a lot since then. But that was just a basic example. Other reasons for counting things, well, in some various biological applications, people look at the way that different species colonise different areas. And you might look at a colonisation pattern and you might want some null hypothesis to say, is this unusual or is this typical somehow? Is there something going on here, some competition? Now, if you take, say, a standard random graph, I'll say a little bit more about what those are, but typically they have their degrees, the number of edges to each vertex is basically pretty much the same for all vertices, pretty close together. but you might have a colonization pattern like this, where there's a bird, say, that for some reason, a very good reason, is going to be occurring in many areas, or you might have an area that doesn't have very many birds in it for a very good reason. And so these things are they're not really unusual. So what should we do? We don't compare just to a standard model of random graphs, and a number of people have suggested comparing to random graphs with the same degree sequence as the data is given. And then you can look at other features of the graph and see whether this random graph is unusual in some way. Now, all I'm going to say about this as far as enumeration goes is that if you want to uniformly generate things, then often the enumeration methods help in that task. There are many things that have been proved, many things about random graphs that have been proved using counting. Even if you restrict to counting by degrees, there's quite a few things that have been proved. For instance, recently, Tran, Vu and Wang extended Wigner's semicircle law for the distribution of eigenvalues of a random d-regular graph as d goes to infinity, and this is extending a result of Mackay for d fixed. And when you're proving things like this, you tend to need to use some enumeration results. There's some very interesting results on sandwiching. Some while ago, Shamir and Upfold showed that basically a random graph of the form GNP, so that's n vertices and each edge occurs with probability p, such a random graph can be coupled with a random d-regular graph with n vertices, such that the GNP is contained in the random d-regular graph. Well, actually they showed it the other way around. They showed the upper bound, that the random regular graph is contained in a coupled GNP prime, where the p prime is such that the density of those two graphs is roughly the same. The GNP prime is slightly denser. And this was improved to a two-sided sandwiching by Kim and Vu, as long as the density or the degrees of the graphs was up to about n to the 1/3. And quite recently this was extended by Dudek, Fries, Ruchinsky and Shilekis to get basically up to very dense graphs. Now, the way they proved it, they remark in their paper that it would have been an alternative way to prove it, and in fact possibly easier, if they'd had enumeration results, which Kim and Vu were using, and which they used in some cases, but they had to get around the problem. They didn't have the enumeration results. Actually, the result they need is now available. So there are many other examples. I'll just mention one more. You've probably heard about you may have heard about the structure of a giant component of this random graph. If you take P such that the average degree is slightly larger than 1, then there's typically a giant component and lots of little subcomponents of size log n in the rest of the graph, small components. Okay, so we might ask, what does that giant component look like? How big is it, and so on, and what's inside it? Well, if you look inside there a bit, you can look at a larger subgraph called the core, a larger subgraph of such that all vertices have degree at least 2, and what's attached to that is a set of trees called the mantle. And then within the core you can look at the vertices of degree 2 and the vertices that are of degree bigger than 2, and all the ones of degree 2 you can sort of suppress and turn that into a graph with min degree at least 3. And we call that the kernel. Then you can ask about what size the kernel has typically and what size the core has and so on. Well, if we start just with the size of the giant component, then some time ago Balabolovich and Tomasz Wójcik sorted out roughly how big that is. It's sharply concentrated. That's the total number of vertices in the giant component. That doesn't say what the distribution is of the numbers around that concentrated point, and that was sorted out for all ranges by Boris Patel and I, that the size of the giant's asymptotically normal. And the way that we proved that was by counting, starting with the kernel, counting graphs with min degree at least 3, in fact counting them by degree sequence and adding up over all possible degree sequences, to see how many of those there were, and then you just count how many ways to add the trees on the outside, and you get an idea of detailed information on the numbers of these things with given size substructures, given size kernel and core. And this detailed enumeration was used heavily by Ding and his co-authors to give a model that you can use to prove things about the random giant component. You can say that you can form a giant component by starting with a random kernel of a certain type and inserting vertices in certain ways in random. So that was just some uses of these results, and I want to turn to telling you what kind of results we have on counting graphs of given degrees. Reed, I guess, started in his PhD thesis by finding an asymptotic formula for 3 regular graphs with n vertices, the number of them. Now, I'm not going to say anything about exact numbers of graphs of given degrees because the formulae turn out to be basically horrible, but you get a much simpler formulae by taking asymptotics in general. And I'd say it's intractable to find nice formulae for the exact numbers for these things, for almost all these things. Okay, so Reed used a method that no one else used. He used Polya's enumeration theory for unlabeled configurations. You might find it a nice exercise to figure out how he could work unlabeled configurations into counting labeled graphs, but he did it. And then at some point, some time later, there were various variations of an idea that was named nicely by Bela Balabash as the configuration model, but in which you take, we're going to take generate a random 6 regular graph in order to count them. We're going to start with 6 buckets with 3 regular graph with 6 vertices. You can start with the 6 buckets of 3 points in each and just generate a random pairing, and if it creates a graph that has no loops or multiple edges, it's good, and you can try to count how many of these pairings create graphs with no loops or multiple edges. And they're what I call, if I say graph in this talk, I mean a graph with no loops or multiple edges, which we call a simple graph. So there were various results giving enumeration of graphs with quite sparse graphs. Bela got up to maximum degree a little over root log n using method of moments and similar things. They're all similar methods here. And this gave a formula for the numbers of graphs with given degrees, actually. Now the formula looks like this. It's not explicit yet, but it's just the number of, that phi is a set of pairings, so the formula is the number of ways you can pair up all the points. Divide by the di factorial. If di is the degree of vertex I, then this factor here accounts for the number of pairings that correspond to each simple graph. And then what's left over is the probability of the event that when you do a random pairing, you don't get any loops or multiple edges. So all we've got to do for any degree sequence, this is an exact equation, and in a sense all we've got to do is find that probability, and then the problem's solved. And the earlier results say, well, if the max di is little over root log n, basically, the probability of that event simple is of this form. Now, the formulae won't be so important. I'm going to show you a few complicated formulae, and that's entirely to emphasize the simpleness of a later formula. So you don't have to read the complicated ones. But this one's in terms of the second moment of the vertex degrees, and M1 is the first moment, in a sense. Okay, from here we started going for higher degrees. Well, McKay got the first big advance. He showed the same formula holds as before when the max degree is around the number of edges to the 1/4. And then I extended that result with McKay a little later to get max degree m to the 1/3, number of edges to the 1/3. And you can see the formula is getting a little bit more complicated. It was clear that if you work very hard, you could extend this formula further and get more complicated formulae, but the amount of work was getting very, very hard, and it looks like no one bothered in the last 28 years to do the next step. there were a couple of results about with strange degree sequences. In particular, Jane Gow and I got a result which covers so-called power law degree sequences that are not covered by these results here. Now they're fairly sparse cases in some sense. The maximum average degree is a little over root n for all those results. If we go up to degrees that are around constant times n, then as long as the degrees don't vary too much, and these degrees, the variation in a random graph is typically around root n. So this easily contains the variation that you typically see in a random graph. So for these degree sequences, here's a formula. Again, just appreciate how complicated it is. Okay. Well, it's not that bad, but it's useful for some things. It has been extended to a wider range of degrees fairly recently, but in particular McKay and ISAF have started using complex martingales to evaluate an integral that I'll show you in a little while later. So there's some interesting work there, but for degrees that are around constant times n, there's no very explicit formula coming from this work. It's a little bit implicit, the formula. Okay, so now after those formulae, we're going to get a rather simpler formula. It turned out that the low degree ones which had big m's all through them and the high degree ones which had some related things, you can re-express those formulae in exactly the same way. So the result that McKay and I noticed is that when the average degree is either quite small, or the maximum degree is quite small, or the average degree, which I've called D here, is close to constant times n, in both cases you get this formula for the number of graphs of given degrees. So this formula works when the graph has degrees or a sum of degree 1 and a few of degree 2, or just as long as the number of edges goes to infinity. Very sparse graph. It also holds asymptotically when you have a very dense graph with all degrees around n over 2. So we could not resist conjecturing that the same formula holds for all densities of graphs, because it's a multivariate formula and it holds in very sparse and very dense cases. Okay, so for regular graphs, it's not very apparent from these conditions, but for regular graphs, say where all vertices have degree d, the gap in the formula is for d slightly bigger than, or around root n, up to n over log n. Now, a few years later, McKay and I showed that this counting conjecture can be expressed in an even nicer way, I think, because, well, if you look at that conjecture, what's the reason that it would hold for such a wide range of values of the density? And this one here, there's a lot more things going on that make it seem reasonable. So the first part of the conjecture is that if you take G and M, which is just a graph with n vertices and m edges added at random, you look at the degrees jointly, the joint degree distribution, then in a quite precise way, that's equivalent to taking n independent binomials, where the p here is just the density of the graph, and then you condition on the sum of those independent binomials being 2m. Then for typical degree sequences, this actually gives the asymptotic formula. You can deduce from the probabilities in the model how many graphs there must be, and it gives you the correct asymptotic formula. So that's for G and M. Now G and P is the graph where you just add edges independently at random with probability P. And actually G and P is composed of a lot of slices of G and M's, if you like, with an appropriate probability distribution over the M. So from this one here you can actually deduce this conjecture here, that G and M is like a whole lot of independent binomial. G and P is a whole lot of independent binomials, bin n minus 1 p hat. Now each vertex degree in G and P is exactly, the distribution of it is exactly, of course, bin of n minus 1 p. But what we do here is we do a De Finetti theorem type distribution, where in advance we choose a random p hat which is actually a truncated normal very close to p. We choose that p hat, and then we generate all the binomials independently with the same p hat, so with the same distribution. So you do that, and then that gives you a good model for the distribution of degrees in GNP. And what we showed, well, the counting conjecture, which we know is valid for very sparse and very dense graphs, implies that these conjectures give you very accurate models of the degrees of the random degree sequence. You can measure the probability of any event that's, you can asymptotically get the probability of any event that's not too rare. And too rare means sort of you can go down to polynomially small probabilities, and it still works. So those conjectures were sitting around for a while. But I guess, the one thing about those conjectures is that when you look at them, this one here, the one that's, if you want to apply them to deduce anything about distributions, the first one conditions on the sum being 2m. And I think there's some interesting things that could be done about that to say how you can condition on the sum being 2m. But the thing that McKay and I focused on was the GNP result, which just requires a sum to be conditioned on being even, because the sum of degrees has to be even anyway. And it also requires you essentially to average over this p hat. And what we did in that old paper, was show how you can take care of those features for many sorts of problems. So what sort of results were known for degree sequences of random graphs? Well, the distribution of a number of vertices of degree k was looked at for a couple of decades by various authors, and results about the nth largest degree. For instance, Baylor's very well-known book on random graphs treats this topic in chapter 3. And it turns out that the machinery that we created, I guess, in that paper in the 90s, does show how you can obtain basically these kinds of results and many, many more, as long as the binomial conjecture is true. So we just have to fill in the binomial conjecture, and then you get a whole lot of results about degree sequences of random graphs. Quite easily, because basically our machinery says for most cases, you just look at independent binomials and you get the answer from that, with a slight adjustment perhaps. Okay, so the recent result is we have filled in the gap now with Anita Liebenau. The conjectured formula for the enumeration result does hold in the gap that was there, and this implies a binomial conjecture holds for all densities. So we can deduce all those results about degree sequences of random graphs from those. I want to look at the approaches used, both the old approaches and new approaches, and I want to say something about the perturbation method in general, because it's a little bit more general than just counting graphs of given degrees. So, as you recall, basically the problem was you're given a set of pairing, you're given a pairing model, this one is configuration model, and you want to count pairings, and I'm going to forget about loops now. Let's just pretend that they don't exist, and we'll just look at counting pairings with no double edges. These guys are bad, and we want to see how many pairings have none of them. Well, if CI is a set of pairings with exactly I double edges, then what McKay's idea was to estimate the ratio of the numbers with CI and CI minus 1. He used switchings, which I'll just describe briefly. You take an element of CI and you choose a random double pair edge, and you take one of those edges and you choose another random pair and swap around in this fashion. And then usually that gives us something in CI minus 1 with one less double edge. If it doesn't, it's bad luck, you have to bound the cases where it doesn't. And then the reverse operation, you can estimate how many ways you can go forwards or backwards. Now, if you look at the ratios of how many ways on average you can go forwards and backwards between two sets like that, then it's like having a big bipartite graph, and you want to look at how many vertices are on one side or the other. You can look at the average degree on one side or the other. Once you know those average degrees, you know the ratios of the numbers on each side. So the same thing happens here. This analysis gives us the ratio of the ratio desired there. Okay, now that ratio actually matches almost exactly the ratio that would happen if the distribution of the number of double edges were a Poisson random variable, and from that you can deduce that it's asymptotically Poisson. All the way down to very accurate estimates of the tail, which goes all the way down to where where you're asking for the probability there are no double edges, even though that's an exponentially small probability. So you get that probability asymptotically this way. And that's how Mackay did the regular case up to n to the 1/3. Actually, I want to make a comment here that I don't think has been really made anywhere before. Stein started working on adapting this. There's a Stein's method of approximation of distributions by normal random variables, and Chen extended that to Poisson. And it turns out that that method is very similar in a way to what's going on here. Stein used some called a sort of test function, and some of the test function is looking at what happens on the boundary of between having, say, less than I double edges, less than I of anything, and the next value, I plus 1. And what happened in 90 is I met Stein, and he was working on exactly this problem of counting graphs of given degrees. And what he'd done, he explains it actually in an earlier paper with Latin rectangles. He took Chen's method, and which was Stein's method, but people, adapted to Poisson. People call it Chen-Stein or Stein-Chen. He took that method and he said, look at this problem. Without all the formalism of the method, what does it suggest to do? And he came up with something which is actually equivalent to this switching thing, only he would write down equations a little bit differently, and he would leave error terms. Instead of writing down error terms, he would tend to keep exact terms for expressions which he bounded later. Now, that description of his work is from reading his paper on Latin rectangles. I didn't ever see him write down things about this problem because when he wasn't aware of a result that Mackay and I already had at that time when we talked to him, and that result was that we got up to graphs of degrees little over root n, counting, finding the probability of the pairings being simple. And the way we did it was by using some different sorts of switchings, which look almost the same, a little bit more complicated, but it turns out that these behave much better in terms of how you can analyse them for counting the number of ways of going backwards. Okay, so what I wanted to say is that Stein's method, actually Chen called Stein's method a perturbation method. So it's not surprising that actually it's very similar when you apply it to this. Well, when you take the ideas and apply them here, you end up with the same thing. So the idea is you perturb you're perturbing the structure slightly, and you're seeing what that implies about the distribution of the probabilities. Now, the approach for very high degrees, that was the low degree case where you have quite sparse graphs. For very high degrees, then Cauchy integrals tend to converge quite nicely, and that's what Mackay and I did in 1990. We evaluated this, asymptotically evaluated the Cauchy integral like that, a multiple integral, an n-dimensional integral. Takes a bit of analysis. Actually something, yeah, okay. Okay, so there are two methods there. Other methods that were used in the past, I mentioned slightly. And now I'm talking about the new approach to counting graphs of given degrees. And this will work actually for very sparse graphs, all the way up to graphs which are almost full density, almost constant times n density. So the idea is it's another perturbation method. We're going to compare things not pairings with different numbers of pairs, but graphs with different degree sequences. How does the number of graphs change if you vary the degree sequence? Now the d minus EA here is the degree sequence. So I've taken d to be a sequence whose sum is odd, and d minus EA you subtract the elementary vector with a 1 in the A position. And same for EB. So we're taking the ratio between numbers of graphs where the degree sequences are as close as possible. Now, if we did a similar thing with a set of points in a probability space that were arranged in a lattice, then what we'll do is look at the ratios between the probabilities of points, say across rows and then down a column. And once you have all that information, then you can look at the ratio between the probability at any point and any other point by telescoping, taking a telescoping product of all those ratios. Well, that's obvious. This is sort of trivial. The reason I'm saying this is that what we have here is an n-dimensional case where the n dimensions is one for each vertex. And we're varying the vertex degrees at every vertex, one at a time, or two at a time, more or less. So the picture is a little bit like this, but with n dimensions. This just tells us what accuracy, we need to know how accurately do we have to estimate those ratios in order to deduce something about asymptotics, to get the main term in asymptotic formulae. And it all boils down to how long is the telescoping product if you go from here through ratios to somewhere else. And since we have n dimensions, and there are arguments to say that we need around root d, if we look at graphs at average degree d, we need around root d possible values of a degree in each dimension. So the telescoping products have lengths about n root d. And as a result, the relative error in each ratio required is a little over 1 over n root d, which is a fairly big ask if you look at the sort of relative errors in quite a lot of combinatorial problems of this nature. So how do we estimate this ratio between the numbers of graphs of given degrees? It's a variation of the switching idea, but it's quite a different kind of switching. You start with a graph with given degrees and you choose a random edge incident with one vertex, let's just say v1, and move it to v2. So there it is, you move it over to v2 from where it was. The other endpoint stays the same. Well, you've got a graph where if the first graph had degrees d minus e2, then the next one has a degree sequence d minus e1. You can look at how many ways you can go back and forth with that switching, and then that lets you estimate the ratios of the things. It looks simple, I hope. Unfortunately, it doesn't turn out too simple. There are bad cases where you take a random edge, and it might happen that there's another edge in the way so that when you do the switching, you get a double edge, and we just have to disallow those. And also there's another case where you can create a loop. How do we disallow them? Well, we take account of how many there are. What's the probability that such a thing will happen if we start with a random graph with this degree sequence? But if we do take account of that, then we get an estimate of the ratio between the number of graphs with degrees d minus e2 and d minus e1. All right, so in the forward direction, you can write it this way. This is how many ways you can do the switching from a vertex of degree d1. And bad means the probability of that bad event happening. Well, the event that switching is disallowed when you take a random edge. And the number of ways backwards is here. So we want the ratio of g of d minus e2 over g of d minus e1. So again, this is just counting the edges in a mega bipartite graph from one side of the graph and then again from the other side of the graph. And you get a ratio there which is a nice formula, but we don't know the probability of this bad event happening. But using some other ideas, it became apparent that what we need to involve also is the probability there's an edge between two given vertices in a graph with a random graph with a given degree sequence. We call that PAB of D. And now we combine with some other combinatorial operations to get relations for this probability, and then we were able to write the probability of this bad event purely in terms of those p functions. That means we get the ratio we want as a function of the p functions, but the p functions we get an equation in terms of the ratios and the p's, which is getting a bit complicated. But once you have formulae like this, you can start expanding in some way. and hoping for the best and trying to get some formula. But a good way to view it, I think, is the right-hand sides here. They're like operators on the functions PAB as a function of degree sequence and RAB as a function of degree sequence. Now, what I've hidden here is actually the probability of bad involves P's, but for different degree sequences from what you started with. So in general terms, what we want now is to find a solution of these, so we want a fixed point of those operators. But when it comes down to the nitty-gritty and you find to define the operators, exactly what domain they're working on, it gets a little bit complicated. But the basic idea is just that we're after a fixed point, and we've got a fixed point in the slides. Do I have some other way to advance? Maybe turn it off and on again? Off and on? Back? Oh, we got there. Okay. Somehow? Well, yes. Thanks. Whatever you did. Okay. So if we're after a fixed point, what we can do is start with a bound on the probability. Almost any bound will do. If you know the probability of an edge is a little over 1 over n. A little over 1, sorry. A little over 1. A fairly weak bound. But there's a combinatorial argument using switchings of the old sort that says the probability of an edge is ordered d over n. And then you can actually iterate these bounds and show that the approximations are getting closer and closer to a fixed point within a tolerance of certain errors that creep in when you try to write this thing down in a useful way. You see, these equations are exact equations, but those degree sequences end up involving all the possible degree sequences of graphs up to that sit below the one you're working with. And the ones that are way out extreme degree sequences, you don't want to look at those. So we do some approximations, and after iterating equations, we guessed what the formulae were to the desired accuracy for these things, and justifying everything, because there's various various truncations of things, requires quite a lot of the usual sort of work we do in probabilistic combinatorics and random graphs, sharp concentration and similar things. Okay, so the idea was simple, but to carry it out required a fair bit of work. I'd like to say a little bit about some special case. So the formula for d-regular graphs, again, is quite simple. And that now holds, we know it holds for all d. That's an asymptotic formula. All d between 1 and n minus 1. Our method extends to bipartite graphs, which extends the results of various authors, and to hypergraphs, which we're still working on. Okay. But these results should, we can get denser results than previous ones there. Our work doesn't extend to the very dense case, where the degrees are around constant times n. One more application, the Latin rectangles. Here's a Latin rectangle, 3 by n. Of course, you know, every row is some permutation of the numbers 1 to n, and every column must contain different numbers in each row. Here are some results on the asymptotic formula for a number of Latin rectangles that are k by n, obtained by various notable people, including Stein, and that was a paper I referred to earlier. Then Godsall and McKay, if you look at the progress here, Godsall and McKay made a very, an intimidating leap. They announced in 84 and the paper appeared in 90 and got up to a formula valid for all k little o of n to the 6/7. And progress stopped there. Note their formula, it's fairly simple. Okay, what's the next step? They conjectured their formula works, that's their formula and that's the true number. They conjectured that they're asymptotically equal when k is less than n to the 1 minus delta for any delta greater than 0. Well, they were right. In fact, it turns out they're true, their formula works all the way up to k is little o of n over log cubed n. But, so with Kevin Leckie, we've got a result there, it's almost completely written up. And the formula is in a different form. It's actually slightly simpler than the Godsell-McKay formula. And, and it's valid for, well, as I say, well past the n to the 1 minus delta. We're just a logarithmic factor below constant times n. and the two formulae there, the Godsell-McKay formula and ours, are asymptotically equal when k is little o of n. No doubt it's, I'm pretty sure it's true for, well, we have some specific conjectures, but it includes the conjecture that they're both correct when k is little o of n. A word about the method here. It's the same method in some sense, because Latin rectangles are edge-coloured bipartite graphs. And so we're going to reduce it to a problem of counting graphs of given degrees. You can see how to make the graph. If you consider each row as a function, then you sort of do a diagram of that function and you get a graph. It's 3 regular in this case, but because of the rules of the Latin rectangle. If you haven't seen that before, it's easy to check out why this is true. So we want to count edge-coloured, k-edge-coloured, k-regular bipartite graphs with n vertices. That's it. How do we do it? Well, they are graphs of given degrees in some sense, but the degree is specified for every single colour, and the degree is very small. It's only 1 in every colour, right? So to get our approach working, what we consider a model for graphs which relaxes some of those constraints. You take bipartite graphs with n vertices on each side, top and bottom, and they're k-edge coloured, but not properly coloured. So the previous one, they were properly coloured, and every colour induced what's called a matching. Here, we don't insist on that. We just have them k-edge coloured, but we make sure that the top vertices do have degree 1 in every colour. Now, this is a fairly straightforward model to analyse. There's enough freedom. They're constrained in the top, but there's a lot of freedom in the bottom, which makes the choices of each vertex up here independent for where the 3 edges go. And all we have to do is ask, what's the probability of a given colour degree sequence in the bottom? We want to know the probability that they're all 1 in every colour down the bottom. Then we'll have what we need. Now, these are graphs. They don't have double edges, and the Latin rectangle has to forbid double edges here. Okay, but we start with these graphs, and we can use the same general approach as we did before. We start switching things around, changing the degrees at the bottom and looking at ratios. How many have this degree sequence compared to one that's just perturbed slightly? Okay, and that all seems to work out fine. I suspect we can get rid of the log cubed and turn it into log squared if we work hard enough, but we'll see. So a few final remarks. Actually, another example of perturbation method, I used not to count graphs exactly, but to, in a sense, it is. If you want to know how many small subgraphs there are in a sparse random graph, then the perturbations you can do here, for instance, how many triangles are there in a sparse random graph typically? What's the probability distribution of the number of triangles? The operation you can do, the combinatorial operation, is just throwing in an extra triangle at random, and then you have graphs which usually have one more triangle, and you can start looking at ratios of how many have a given number of triangles compared to one more. And this turned out to give some new results for distributions of subgraphs of random graphs. Again, you end up getting something that looks like there are these operators, then you want to get close to a fixed point, but there are extra complications in that case, and the way that we justified everything was quite different from this one in the graph case that I've been talking about today. So here's a few unsolved problems just to give you an idea that we don't know everything yet. It'd be nice if degree sequences like those ones that I mentioned, there's some power law degree sequences that are a bit weird, and the formulae for the numbers there are different. It'd be nice if there's some approximation by something like binomials, where you take some model and generate random degree sequences, and you can say how those degree sequences are arising really. In particular, it'll just solve the enumeration problem. If you know about the parameter in power law degree sequences, then for mu less than 2.5, we haven't got an answer yet for how many graphs there are asymptotically with a given degree sequence that looks like a power law. Latin squares is a big problem. We got up to n over log cubed n. If you can go all the way up to n by n Latin rectangles, then you've got Latin squares, and the question of how many of those are there has been looked at by many people. An example of something that's somehow similar, but I don't know whether any methods I've talked about might apply to it, really. The number of connected graphs of the given degree sequence. And another sparse question, if you have a sparse acyclic diagram, well, given degrees, in degrees and out degrees, and if the average degree is constant times n, no, not the average degree, the number of edges is constant times n. How many are there? That's not known either, really. No good answer for that. Okay, I'll have to leave it there. Thank you.
Thank you very much indeed for the lovely talk. So, are there any questions? Yes, Peter.
Is it plausible that a refinement of this method could solve enumeration of Latin squares? The perturbation method you described, for counting Latin rectangles.
Okay, let's try this. Solving Latin squares, yeah. So that's what we were trying to do in some sense, right? And it doesn't seem to extend that far. Similarly, it seems to be very hard to get it. That's a similar problem to trying to extend it to count graphs that are very dense, let's say average degree d over n over 2. And there may be a way to tweak things, but we haven't figured out a way to there's a really new idea needed there to do that.
Is there another question? If not, then let us thank Nick Wormald for his wonderful talk.